organizer of this nice program and for giving me the opportunity to give this talk, and well, to all of you for attending this talk late in the afternoon. So I will tell you about some stuff about cyclic computation, and this is something that I've been working on with various people in the last year, but I will mostly tell you about some work done by our PhD student who recently finished, Bartosz Szczesny, and whom I supervised together with Alastair Rutledge in Leeds. So the general context can be summarized, the general context and general motivation for this type of research can be summarized by this question: what determines species diversity? So this is, I won't answer this obviously. This is a question that was listed in the last, in 2005 by Science magazine as one of the big science questions that science faces. And probably it's still there. It's still a very important question still now. So, well, the approach here will be much more prosaic, and I will tell you basically three things. So I will first just give you an overview of some biological experiments on some microbial communities that inspired our work, and then I will tell you about the first series of theoretical work that I essentially did with these people here, mostly with Tobias Eichenbach and Edward Fry, first in Munich at the time, and then also with Johan He and Uwe Tober, who are at Virginia Tech. So in this first part, I will tell you about the role of mobility and how this affects, influences the properties of extinction in this class of models. And in the second part, or in the third part actually, of the talk, I will tell you about some of this more recent work and a new approach on this type of models. And this new approach, we believe that we have put forward a method to characterize more carefully the patterns that are formed in this class of models. And basically, we try to answer this question here: when does cyclic dominance lead to spiral waves? So, first, the first part. So, as I told you, well, obviously there is a lot of interest in trying to understand the mechanisms that allow to maintain biodiversity, and this has motivated a large body of work. And an influential set of experiments were concerned with a microbial community of E. coli, with 3 strains of E. coli. So this experiment, there were one strain of E. coli that was a toxin-producing strain. So basically, this strain was carrying a cold plasmid and releasing a poison, and it was also producing an antidote, so it was not committing suicide, right? So this is the strain here called C. There are also colicin-sensitive bacteria. These are just killed by the poison released by this strain. And eventually, there are also resistant strains, so resistant bacteria. And these are just strains that have the antidote, so they pay to produce the antidote, but they don't produce the toxin, right? So what happens is that C here kills the sensitive strain S, right? And S outgrow R because R has to produce the antidote, so it has a price to pay in terms of fitness, right, to produce the antidote. So S outgrow R, and on the other hand, R outcompete C because it has the antidote, but it doesn't need to pay to produce the toxin, right? So this community is engaged in this cyclic competition where C dominates over S, S dominates over R, R over C, right?
Is the immunity protein released?
Sorry?
Is the immunity protein a public good or is it localized too?
I don't know.
Is the immunity protein released into the environment or is it?
No, it's not really. So, they produce their own protein.
I see. So then how does S outcompete R?
It just in terms of reproduction rate.
In a non-Collison environment? In which environment?
Oh, well, this is coming.
Okay.
Yeah. So it was suggested that this could be modeled by this in terms of rock paper scissors game, which is this metaphor for cyclic competition, right? And where rock crushes scissors, scissors cut paper, and paper wraps rock. So perhaps I should get rid of this, right? It better. So should I just go like this? Okay, it's better now. Okay, so yeah, the question where? So that's exactly the right question. So these people carried out these experiments first on on a petri dish, so on plates, and in flasks, right? And they observed very different outcomes. So in flasks, what they realized is that very quickly, one species dominates over the other, and two go extinct. So here, this is the resistant strain that survive, and the two other go extinct very quickly. Whereas on petri dishes, well, it turns out that for a long time, well, the three strains coexist, and they form, well, some sort of clumps and patches here, right? So, well, this is something interesting because it has long been conjectured that space and local interaction matter in terms of maintenance of coexistence, right? But as Novak and Sigmund put it in the comment on that Nature paper, this series of experiments by Kerr et al. Gives a new impetus to investigation by stressing the importance of geometry in neighborhoods. And so they had this comparison. So basically they said that many habitats resemble the surface of a pizza more than a bowl of soup, right? So basically, yeah, this is more pizza than a soup. But yeah, the important thing is that in terms of coexistence, there is a huge difference between implementing the dynamics on the flask, which is something that we usually model in terms of ODEs and mean field, rather than what happens on a static plate, where we have to resort to more advanced mathematical modeling methods, right? So that's where we are going. Also, this type of cyclic competition between three species, it's very simple, but it has also been observed in other systems. So here there is also a sort of famous paper by Cinervo in 1996, where we observed that the mating strategies of these lizards, Californian lizards, obey this cyclic competition. So these are color-coded lizards, if I remember correctly. Well, again, yeah, this should be orange, this is blue, this is yellow, and this guy dominates over this one over that one, and vice versa. Okay, so what I want to tell you now is Well, so obviously this has motivated a lot of work from a theoretical perspective and try to understand really how to explain such a difference between what happens in the flask and what happens on the Petri dish. So what we came up with is a very simple model. So it's a spatial version of a simplification of a famous model by May and Leonard, Lord May, that we saw yesterday, with mobility, with pair exchange. So basically we have three species in competition. Right. Okay. We have three species in competition, empty sites in black, right? And we will say that basically there is cyclic dominance, there is reproduction, and we say also that individuals can move. So cyclic dominance, we say that red dominates over blue. So when they interact among nearest neighbor, right? We'll say that red displaces blue, right? That becomes an empty site, right? Blue displaces yellow, and yellow displaces red. This cyclic competition. We also say that all these three species can reproduce when there is space nearby. And we want also to include some form of mobility, and we want to do this in the simplest way. So we just say that any neighboring site, individuals, can swap its position with its neighbor, nearest neighbor, right? So we can just swap these guys. The important thing is that they are nearest neighbor. Right. So, and we do that on a square lattice. So just as a warm-up, and useful warm-up actually, it's useful to keep in mind, to see what happens in the well-mixed case, so at the mean field level. So this is essentially what would happen in the flask, right? So there, when everything is well-mixed, so basically space does not matter anymore, right? The only thing that matters is cyclic competition and reproduction. So these are the species. So I is 1, 2, or 3, species 1, 2, or 3. This says that species 1 dominates over species I plus 1, right? So it displaces species I plus 1 with some rate sigma, and this is just reproduction, right? And we just say that species R 3 plus 1 is just species 1. We have this cyclic thing, and species 1 minus 1 is just species 3. We just, yes, so.
Given the biology that's inspired this, it sounds more like it's the one which wins the competition actually invades the other.
Mm.
So would it make a difference if instead you have S plus SI plus 1 goes to SI?
Yes, okay.
SI plus
So this is something that I will discuss. So a lot of, so you say here, if we say, instead of empty set here, we would have SI.
Yeah.
Yeah, so yes and no. So what I'm going to discuss is in the next slide is a generalization where we have this and that. So this is really the main Leonard model, and the one that you say, you refer to, is usually what people, is essentially the zero-sum rock, paper, scissors game. So it's a bit special in the sense that it has, at the mean field level, there is a concept of motion for the model that you are referring to. So it's a bit special, right? So what we do then, a lot of people indeed are interested in the model that you are referring to, which is mathematically special but is popular because it's simpler, is to combine this. This is something that I'm going to elaborate in the next slide. So it's to combine this form of selection, cyclic competition, with the one that you just mentioned, which is this one, but instead of having here an empty space, we would have another SI. And we are going to see that when we have that, then, we are going to see what happens. So this is covered in the next slide. But in the first instance, we studied this because, as I said, at mean field level, this is less pathology or less spatial than the model you are referring to. And so what happens is, if you study the the mean field dynamics. So if you write down the ODEs corresponding to this type of dynamics, you find that there is a reactive fixed point that is unstable, and the dynamics takes place on an invariant manifold here, known as this yellow manifold here, and quickly the trajectories approaches the edges of the phase portrait, and they form these heteroclinic cycles, right? So what happens is that you start somewhere, and you start approaching the edges of your phase portrait, and you approach them, but you never reach them. So basically, what happens? You are approaching a system where there are almost only one of each species, and you spend a long time there, and then this goes to zero, and another species seems to take over, and then goes down to zero, and another one, and so on. Okay, so that's nice, but any finite size fluctuation will bring this to an end, because any finite size fluctuation will push you to the boundary, and then you are stuck in one of these absorbing states. So basically, if you don't have spatial structure, right, as in the flask experiment, where very quickly one species takes over, right?
There have also been some other solutions for this issue, right? A small source input, like
Okay.
a seed bank,
Yes.
will also stabilize the
Okay.
dynamic.
Yes. Yeah. There are various ways of stabilizing. Yeah. Okay. But for this model itself, per se.
Yeah, the
Yeah.
pure model itself.
Yeah.
It leads to the boundary.
Yeah. Now I want to take this model and to consider a spatial version of it and see what happens, right? So actually, this has been done. So we have just seen that the well-mixed case, there is loss of biodiversity or coexistence in finite time, right? So that's the mean field case. In the case where individuals are immobile on the lattice, so basically when we have this cyclic competition and reproduction, but no mobility, so they cannot move, they cannot swap the position. Well, Doret and Levin showed that essentially numerically that this led to noisy patches, right? And what we have done here is to investigate what happens when we have this pair exchange, right? And what happens is that when we have this pair exchange, it turns out that these species coexist first, and they form this entanglement of spirals, as you can see here. So each color corresponds to one species. And when we increase this mobility rate, well, the size of the spiral grows, and at some point, there is one giant spiral that outgrows your lattice size, and this leads to one species taking over, right? So to rationalize this, what we did was to compute the probability that after a time of the size of the system, just one species survives, and we see that there is this critical value for the mobility rate here, dc. You see, when you are below that, you are in this region here, right, where the three species coexist, and all of a sudden, this becomes essentially 1, right? And this transition becomes sharper and sharper when your system size grows, right? So, so how we wanted to understand how we can predict this transition. So what we did was to combine various approaches. So we used lattice simulation, insight from the mean field equations, treatment, partial differential equation, and also a tool called complex Ginzburg-Landau equation. I don't know if you are familiar with, but this is coming back soon. And basically what we did, I won't go into the details right now, because I want to show you something that I think is better. We were able to obtain this state diagram. So essentially, we were able to predict where in the space of the parameters where there is uniformity and where there is coexistence, right? So in this region here, the three species would happily coexist, whereas here there would be just one species taking over, right? So that's very nice, and well, we made it in nature, so it was very nice. But there are some limitations.
Sorry, so there's a theory. So the red line is a theory, or?
Yeah. So okay, right. So the red line is prediction based. Yeah, here, red line. Yeah, the red line is a curve obtained from an analytical treatment that I'm now criticizing here. So what we did to obtain actually this red line was to do various approximations, and mostly these are uncontrolled. So basically we ignored a lot of nonlinearities. We treated these heterochronic cycles as limit cycles, and in this way, well, we approximated the partial differential equation corresponding to the reaction I showed you, which by the way were derived in an uncontrolled way. Still, we approximate this uncontrolled PDE as an uncontrolled complex Landau equation that I'm going to discuss soon. And on top of that, we use one parameter that we had to fit. So that's where this comes from. So there was room for improvement, right? And so that's what I'm now going to discuss, how to improve it on this. So what I'm willing to do now is to tell you a bit more about, I'm interested in characterizing this, these patterns here, right? And the approach that we are doing now is to adopt another route and to use a metapopulation approach. So basically what we do is actually a little bit like something that Alan has been doing for a while, and also Nigel Goldenfeld we had here has been doing. So it's to consider a grid, right, two-dimensional grid of patches like this, and each patch has a carrying capacity n, right, and we will assume that n, well, it's finite, but we'll assume that n is large, right, and we will do an expansion in n, right. So, right, in each of these patch, we say that, sorry, yeah, we say that in each patch there is, to answer actually Steve's question, there are the following reactions that take place. So in each patch is well mixed. So it's a flask, right? And in each flask, in each flask or in each patch, there is cyclic competition in the form that we just discussed before, right? Si displaces Si plus 1 with the same rate as before, sigma. In addition, we also say, this is probably what you refer to, right? We also say that Si interact with Si plus 1, dominates Si plus 1 by just eliminating Si plus 1 and reproducing at this by just substituting it, right? This is what you were referring to.
Yeah.
Okay. So now we have both of them. Right? So basically, if I put sigma equals 0, I'm just left with the one that you were referring to. But in general, I'm interested in getting sigma and zeta together, right? And the new ingredient here, on top of that one, is the fact that we allow for some mutation. So Si can mutate into Si plus 1 or Si minus 1, right? Any other species. Right. So when I say that, I'm not talking about rabbit being mutating into cows or something like this. It's bacteria, and also these lizards are also been found to undergo this kind of mutations.
Do you have natural death rate in the model?
I don't have a specific death rate, no.
So, okay, so
It's all by selection.
by killing or eating.
Yeah, by this kind of.
Yeah.
So that's what happens in each of this patch. On top of that, now to implement the dynamic, well, all of this happens in each of this patch, right? Now, to allow for some form of mobility, we say that we have pair exchange, like before, and also we allow for some hopping. So basically, what we say is the following. We divorce what we had before. We say that here, so, oh, sorry, here, okay, with some weight delta D, right? One individual here of species 1, 2, or 3 can swap its position with an empty site. So basically, it can go from here to there by leaving an empty site an empty space in the patch with some delta D. And on top of that, we also say that, as before, any of these species can swap its position with any neighboring, with any individuals of a neighboring patch, right? So basically, we divorce what we had before. Before, we just pick randomly one guy from one side, another one, and we just exchange. Now, we have two different rates, right? And we make a distinction between swapping between two individuals and hopping on an empty space. And this we are going to see that this brings about nonlinear diffusion. So just to make it clear, before we had delta D equal delta E. Now we have just divorced this. Yes.
So the hopping would be something like an immigration or something.
Sorry.
The hopping would be a sort of an immigration, or what would be like the natural setting for the hopping?
So what I was what we were thinking of here when we did that was to say that we wanted a simple way to mimic nonlinear mobility. So this kind of models, the mobility is usually nonlinear, right? And so we wanted a way to mimic the fact that when you have you move differently, this guy would move differently in a system which is crowded, or and a system which is diluted, right? So basically, if there are a lot of species, a lot of individuals, well, you are more likely. So there are very few empty spaces. You are more likely to move according to delta E, so just by changing, rather than you have very few empty spaces, so you are unlikely to move by hopping on something because, well, you don't have space, right? And vice versa. I don't know if. So, right. So basically, this is the model. So we again have these three species. Now we have this essentially with cyclic competition and reproduction and mutation within each of these patch, which is well mixed, has a current capacity n, right? And between each of them, they can be between each neighboring patch. There is this mobility, so these individuals can move by either pair exchange or hopping with these two different rates. And if we write down the mean field equations, again the ODEs, we find that the system is characterized by a Hopf bifurcation and a limit cycle. And this is nice because this will allow us to properly derive this CGLE that I was referring to before, right? So this is also why this mutation rate is useful. If this was strictly zero, well, I wouldn't have a Hopf bifurcation. I would just be left with this heteroclinic cycle, which is, well, nice, but won't allow me to do what I'm just going to discuss now. So this metapopulation formulation is nice because it allows a neat connection with between stochastic and deterministic dynamics. And for this, I think we heard already in this program how to proceed. Well, basically you can write down the master equation that describes the dynamics of a system, which is this is something that in principle you can write down, but it's difficult to handle. So a way to go ahead is to proceed with a system size expansion in 1 over n. So n is the carrying capacity of each of these patch. That's why I told you that we assume that this is large, right? Finite but large. And when you do that, to the lowest order, you get the PDEs that are obeyed by the density of each species, right? And this is what this PDEs look like. So it's a system of 3 PDEs. In red here, one has the, so rho here is just the sum of all density. So in red and green, we have here the ODE's equation, if you just omit for now the special thing. So this corresponds to the Milfield equation, right? So this corresponds to just the mutation, and this corresponds to essentially to the May-Leonard model, right? So if you account also for this mobility, right? You have also this this term here, where you notice here a linear diffusive term, as usual, plus here a term which is nonlinear, right? And so this tells you that when delta E is different from delta D, well, we have a nonlinear mobility, right? So there is this rho times Laplacian minus SE times Laplacian of rho, which is definitely nonlinear, and we are going to see how this affects the property of the system. In principle, we can go further, and to the next order, one can derive a Fokker-Planck equation to capture the fluctuations, and for instance, try to compute the power spectrum or things like this. This is not something that we have been doing. And I will now just essentially focus on this PDE, this set of PDE, and show you how one can go ahead and characterize the spalling patterns that we observe in this system by approximating this, by deriving a CGLE that approximates these PDEs, right? And therefore, we will be able to answer this question, well, at least contribute to answer this question. So, so the approach is the following. So we want to derive a complex Ginzburg-Landau equation. So I'm going to show you what it is very soon. So what we do is, first for convenience, it's useful to do the following transformation. S is just the vector with S1, S2, and S3 as entries. So we just do this linear transformation from S to U. And then we do a multiscale expansion around the whole bifurcation in terms of a small parameter epsilon here, which is just square root of mu minus mu h. We introduce the slow variables capital T, which is epsilon square t, which is time, and capital X, which is epsilon times x. Right? So these are the new time and space variables. We just then take substitute u into the PDEs here, right, and proceed by orders. And when you do that, at some point there is a secular term. So a secular term is essentially a term that you don't want in your expansion, right, because it explodes. So you essentially do an asymptotic perturbation expansion, and at some point you end up with a secular term, which is essentially a term like t times sine t or t cos t. And you just demand that this term has to disappear, and in doing that, you end up with the following equation for the amplitude of your, sorry, for the amplitude A, right? So this is our complex being put into our equation. And this equation, well, where delta is defined here and C is defined here, so these are complicated, well, this is complicated expression of the various parameters. This is a different expression than the one that we used in our earlier work, actually. Even though it's relatively close, surprisingly, you know. Anyway, now we have a proper.
Mauro, you've lost your microphone. I don't know if you need it, but I don't know if you can hear me.
Well, probably. Well, I'm not sure. Yeah, I don't know what. Okay, we'll see what happens. Yeah, probably a step on. Sorry about that. So this CGLE is has been derived now properly, I think. Near the Hubble application. So this is something that is supposed to help us understand what happens near the Hubble application, right? And so the first thing I want to show you is that, okay, what I have to show you, there are various things I have to show you. I have to show you that the PDs give you a good description of the lattice system, right? And then, as the CGLE is a good approximation of the PD near the Hubble application, I can argue that I can use the CGLE to characterize what happens, right? So let me show you first what happens if everything works as it should. Okay. So what happens here? Okay. So here we have the lattice system, right, for various values of n, right? So n is 4, 16, 64, and so on and so forth. And here, this is the PD. Right? So you see that when we increase n, indeed, well, visually, this resembles really what the PD predicts for you, right? So this is, well, obviously when we have just 4, the expansion doesn't make much sense, and we have these noisy patches, even though you can perhaps, already when you have 16, we can argue that we see some sort of spiraling patterns here, right? Right, and you notice that it's not just that it looks the same, but you can notice that the characteristics, so the wavelength and things like this, between this, the prediction of the PDEs, so the solution of the PDEs and what your lattice simulation tells you is a perfect match almost, right? So what I'm arguing is that we have a very good agreement between the PDEs and the lattice simulation already when n is above 20, so, and whereas there are some noisy patterns when n is between 4 and 16, right? So with this in mind, I'm going now to use the prediction of the CGLE. So the CGLE is an equation that is around for a very long time, and it has been studied by physics and math by various people for, 15 years or so? 50 years or so? Yeah. It keeps popping up all over the places. Anyway, so a lot is known. So, and in particular, the 2D phase diagram is well known. So what I'm going to do is to use the characteristic of our CGLE to predict what happens, the phase that occur near the Hubble application. And in doing so, so that's basically what the phase diagram that we obtain from the CGLE. Oh, again. Right. So the CGD predict that there are 4 phases, right? So there should be a phase called AI, so in which the spirals are unstable. EI, in which the spiral waves are convectively unstable. Phase BS, in which the spiral waves are stable. And eventually, phase SA, in which the spirals collide and annihilate. That's the prediction that one obtained from the CGD just by just going to the literature and using these expressions for to derive this phase diagram. And this is what we obtain in each of these phases for using our PDEs and then our Leeds simulations, right? So perhaps I can show you the movies so that you see this up. So these are from Leeds simulations. So this is just speed up a little bit. So here, so you see this spiraling pattern, but here this will be the absolute the phase in which spiral waves are absolutely unstable. This will be the phase in which the spiral wave will be convectively unstable. Here they will be stable, and here you can already see that they collide and annihilate, and basically you have just one species that takes over in turn, right? So if you just wait a little bit and just take a snapshot here, the principle here should be a mess. Here, one should observe well-behaved spirals. Here, well, no spirals at all because they just collide and annihilate. And here there is this convectively unstable phase in which spirals are stretched and deformed. So that's what we observe using the Leeds simulations, and this is what we have using the PDEs. So for the same system, well, obviously here we don't have n, right, but the same over parameters. Perhaps I can speed up a little bit. So these are our various phases. So here we have our well-behaved spiral wave. So that's the bound state phase. Here they should be the spiral wave should be unstable, and here they should be deformed. That's more or less what we see. And here they collide and annihilate. So this is a pretty good match of what happened on our Leeds, right? So what we can now do is to characterize each of these phases. So in the bound state phase, right, we can just do a plane wave ansatz, right, away from the core, and from there obtain the wavelength, and by doing so, we also notice that the wave numbers varies with C. So this is what we show here. So this is, so that's the amplitude A, that is approximately R when we do this plane wave ansatz. And in the bound state phase, so which is 0.85 and 1.125 here, you see that A and R varies with the CGD parameter C. right? And indeed, we see that here we have plotted the wavelength as obtained from the CGLE, and we have compared the prediction obtained from the CGLE with what we obtained in our latest simulations and in the PDEs. And well, here in yellow, you have our predictions, well, the theoretical prediction, and you see there is a pretty good match with what we observe in the PDEs and also in the latest simulations here. So essentially, in the bound state phase, the analysis is pretty easy. We can just plug in a plane wave ansatz and obtain all the information from the dispersion relation. Then there is the Ekalund stability phase, and in this case, what happens is that there is an instability that grows, and that is convected away. So what happens is that near the core, we can still use the CGLE and the prediction and the plane wave ansatz to predict what happens and obtain an estimate of the wavelength, which is just shorter than what we obtained in the bound state phase. But away from the core, as the instability is carried away, what happens is, so that's the same system for different times, right? And as time goes on, you see there is the instability is carried away, and then there is a far field breakup away from the core, right? We've also been able to obtain the boundary here, this boundary separating the EI and bound state phase using a technical criterion, but perhaps I just move on and go over the other phase. Right, so there is also a spiral annihilation phase, as I told you, and to characterize the spiral annihilation phase, what we have done is to track what we call the core area. So basically, we counted the number of pixels corresponding to A, to the modulus of A square, or the modulus of A, to be less than some number. So here, 0.25. We have tried with all the values and obtained more or less the same result. And have observed that the decay of this core area has this form here. There is this staggered decay. So basically, what happens is shown here with these 4 pairs of spirals. So what is plotted here is essentially the dots here correspond to these core areas. So that's where you have this the core of your spirals, right? And this, as time goes on, this approach, they meet and they annihilate, right? And you have this the total core area goes down, and if you wait long enough, they will annihilate. Right? And it turns out that when you approach,
What is C?
sorry,
What is C?
what is T? Oh, it's time.
No, C. 0, C, 0.845. So that's
Oh, C, sorry. C is the CGLE parameter. So it's this complicated expression here.
all right.
So
So
yeah,
there's no-
unfortunately, yeah. So the thing is, this is simpler than the PDEs, but all of this boils down to this parameter.
Right. I
And
was hoping for some biological interpretation.
yeah, I also would, but this is yeah.
Speed of light.
Yeah.
And notice all what I'm saying is for sigma and zeta between 0 and 4, because this, if you plot it, you can have complicated well, if you restrict sigma and zeta between 0 and 4, this is relatively simple. You have this as a relatively simple shape. Otherwise, things can become even more complicated than what I'm showing you. So yeah. what happens is that as we approach the boundary, so obviously, so we are here, we are spiral annihilation phase. So when we approach this boundary here, so we approach the bound state, the time necessary for annihilation goes to infinity. So what I'm showing you in this diagram, so the time depends a lot on this value of c, right? So when you approach that value, which is 0.8, well, the time is very large. So here, I think it's c is 0.4, here it should be 0.1. And it tends to infinity when we approach the boundary of the bound state. Finally, there is also the instability phase, right? In the instability phase, well, we also have a local perturbation, but now these local perturbations are not carried away, so they go locally, and these disrupt your spiral waves, so the arms cannot sustain, the core cannot sustain the arm of your spiral, and these are, well, absolutely unstable, so, well, it's a mess. So this is the Eckhouse instability phase, where you still see some deformed spirals, whereas here, deep in the absolute instability phase, well, you essentially see a mess. Now, to make a connection with what Steve asked me, when zeta is much bigger than sigma, so basically in this diagram here, so when zeta is much greater than sigma, we are always in this absolutely instable AI phase. So basically there are no stable spirals. So
Is that because you've assumed that the only source of mortality in your system is when two different types meet and they are either going to lose one of them?
I think that's related to. Well, I was thinking about it in terms of CGLE and so, but yeah, perhaps that's it. What I know is that a lot of people studied the system with sigma 0 and zeta something, to the model that you were referring to, and in all their simulation they never observed spiral waves, stable spiral waves. It's always a mess. And in this model where you have both, you see that when you have only, when sigma goes to 0 and you have zeta, well, you are always in this phase, near the Hubble bifurcation. So this is an explanation, well, I think, for what this guy observed. Now, perhaps in the last, 10 minutes or so, I want to briefly tell you about what happens at low mutation rate. Because all what I told you is near the Hubble bifurcation, right? And one is also interested in what happens when the mutation rate is low. And in this case, well, epsilon, which is proportional to square root of mu minus mu h, becomes of order 1. And in principle, all what I've told you, the CGLA business and this expansion should break down. Okay, that's in principle right, but I'm going to argue that we can still learn something from what I just showed you. So first of all, what happens is that out of the 4 phases that I just told you about, 3 are still here. So we still have the absolute instability phase, the Eckhouse instability phase, and the bound state phase. Now what is missing is the spiral annihilation phase. And this spiral annihilation phase now is replaced by an extended bound state phase. So essentially, what happens is that spiral waves are still stable in what was previously the spiral annihilation phase, right? This is true provided that the dominance rate is not too high, as I will perhaps show you very soon. Now, what we can do with the CGLE is the following. So we are interested in knowing what happens to the wavelength in the EI and bound state phases. And what happens is that, well, just by comparing what we obtain near the hub application from what we have obtained away from it, we notice that just by reducing mu, we lower the value of a wavelength. And what happens is the following. If we plot the various values of the wavelength for a given set of parameters and vary just, say here, zeta and mu, so here we are near the hub bifurcation, and we can use the CGLE to make our prediction. So these squares here are prediction of the CGLE. Away from it, well, we have used the PDEs, so these are the bullets here. And we see that when we reduce mu and mu goes to 0, this approaches a constant value, say lambda tilde. And this tells us that basically you can use the prediction from the CGLE and simulation from the PDE to obtain at some non-zero value of mutation rate mu to extrapolate the value of your wavelength at mu equals 0. Right? But overall, what happens is that by lowering mu, you lower the value of your wavelength. Now, I want to just tell you about a few surprising things. So one is concerned with the mobility. So you know, I told you that we wanted to divorce hopping and pair exchange, right? To have this nonlinear mobility term when delta E is different from delta D. And we have seen that in the CGLE there is this simple effective mobility rate, which is linear. Perhaps let me just remind you this just to appreciate. So here the mobility is linear. Near the hub bifurcation, there is no effect of this nonlinear mobility. Everything is boiled down into this parameter delta, which is a combination of delta E and delta D, right? This is no longer valid when we are away from the hub bifurcation, and this is shown in this picture here. So here we have delta E equals delta D equals 0.5, right? And so everything is linear. Well, mobility is linear, and you have these well-behaved spirals. Here delta D is 1 and delta E is 0.5. Here delta D is 1.5 and delta D is 2. Delta E is always 0.5. And you see that what happens is that you have this far field breakup of this spiral wave. So perhaps I can show you a movie illustrating this. No, it's not this one. It's not this one. Oh, okay. So here, it's linear mobility. Here, it's nonlinear mobility, and all the parameters are the same. And you see that after some time, you have.
Sorry,
these.
I have to say, you are in my power.
What?
Sorry.
Oh, okay. Okay, now it's coming. You see, you have this far field breakup now occurring. So this is just to illustrate what is the effect of this nonlinear mobility. And there is another surprising thing that occurs when we increase this sigma. So the sigma is this dominance rate. And I told you that away from the hub bifurcation, the previous SA phase this annihilation phase is replaced by a well-behaved extended bound state phase. This is shown here. But actually, it's not totally true, because if we keep increasing this rate sigma, keeping the other ones set to 1, say, so if this is much larger than the other rates, what happens is that this spiral wave again becomes unstable. So there is again this far field breakup of these spiral waves, and you have this myriad of spirals occurring when sigma is much greater than the other rate set to 1.5. Perhaps the very last thing I wanted to tell you is is about the role of noise. So up to now, I essentially said very little about noise in this metapopulation treatment, right? And all what I told you comes essentially from the analysis of this PDE obtained from the CGLE. And this is fine, and as I try to argue, useful and faithful, provided that the patterns are not too small. What does it mean? Well, this is illustrated here. So if the patterns are small, you may end up with a system that whose description in terms of PDEs gives rise to the following set of messy spiraling patterns, as you see here. This is obtained from the PDEs. And this is typically something that we obtain when the diffusion rate, the mobility rate is very small, so 0.05 here. So when the mobility rate is very small, the size of your spiraling pattern, that is proportional to essentially square root of delta, is very small. And if you do a simulation with your PDEs, provided that you have a good enough resolution, you can still see, or you can still get some spiraling patterns here. Whereas if you use the same system on a lattice, well, you see just noisy patches, right? And this is because simply now the wavelength here would be too short to be to obtain a good resolution on the lattice. So here you can arguably not see any spiraling patterns. So that's typically one of the cases where the CGLE and the PDE cannot help you describe what happens here. Okay, so just time to wrap it up. So I try to show you that well, local interactions are important to explain species coexistence in this simple model inspired by this cyclic compilation in E. coli. And then I try to introduce this metapopulation formulation of a model that allows, I think, a neat derivation of the PDEs and of the CGLE of the system that allows you to characterize carefully the phase diagram of what happens in the system, phase diagram of the system near the hub bifurcation, and from there you can also infer what happens away from that hub bifurcation. We have seen interesting phenomena like far field breakup, both in the 8070 phase and due to mobility, high dominance rate, and this gives us a good description of what happens in the model. Now, a question that one may want to address is, well, how does this relate to what these guys have done in their experiments? And because as you may have realized, well, it's hard to see any form of spirals in here. Right? So is it because, we are, this corresponds to a phase in which spiral would be unstable, or is it just a matter of time scale, or is it just that the model is oversimplified? Probably.
Clearly the time scale, right?
Hmm?
It's clearly the time scale.
Obviously.
Because you can see that the sea hardly, if you look at one of these types, they've hardly moved.
Also,
Probably.
the spatial scale, you just don't have enough
Also,
patches on there.
But those things don't eat each other. They're inhibiting growth.
Yeah.
So it's like you have something here, something there. This one grows, it doesn't. So it's a little bit different than
It's,
the placement.
yeah. So how they carried out their experiment is also, so they had the cloth, so and they just put the cloth on the plate and then move it a little bit. So it's obviously hard to see how this fit the model, or how the model fit what they have done. Yeah, and
Mauro, sorry, you're taking questions yet?
oh yeah, I'm happy to.
So I don't know if you've got something to explain diversity, but you have certainly a suite of rules to get three almost identical species to partition. So it may or may not be a great diversity thing, it'd be a brilliant synthetic biology thing. Because if you could actually get to the biological basis of the parameters, and you're working with E. coli, which is one of the easiest organisms to work with, you could actually, if you could get a sort of a really good E. coli person, you could, they should be able to actually, at least in principle, treat the parameters in the E. coli to actually test your model in a real system.
So yeah, I know that these people with whom I did the first works in Munich, they tried very hard. Well, they tried. The story is that we went there to see the experimentalists before submitting this to nature, and they laughed at us. And then we had this.
This is Brendan Bohannon's group, isn't it?
Sorry?
Is that Brendan Bohannon's group?
Yeah.
Yeah.
Well, we didn't go to them. We went to local people in Munich, and they didn't want to do it. It was a waste of time. Then this went out, and they were very happy to come. But what they tried for years now, it seems, and it seems that the very hard thing is that basically the E. coli, the bacteria, seems to be lazy. They don't want to move. So we in the paper we try to argue that actually we understand what happens when you change mobility, right? And here, if you read the paper, they essentially say that everything is immobile. So they have, right? And so you try to argue that if you put this on soft agar, super soft agar, perhaps they wouldn't. They tried, and apparently they keep being lazy. So it is, yeah.
That's strange because they actually swim and swarm on plates.
Yeah.
Bacteria. I mean, you can show that.
So I don't know. Well, that's what.
That's very weird. I mean, maybe we're taking some mutations on the
So you think this could be?
Well, I mean, they
could
do
be
move.
realized.
I mean, you can check pictures of bacteria swarming on the surface of the agar.
Yeah.
That's
Yeah,
with
it's
modifying the sugar on the LV and the
so. But
media. And they can swim.
also for this community here, you.
Not under these conditions.
Yeah,
They
okay,
will
so-
not move under these conditions.
Well,
Well, move far, but they might move a little bit.
well,
Not really.
maybe the diffusion
This
of the
is
toxin
hard,
is
this is hard agar, E. coli on hard
Yeah,
agar
sharp.
doesn't move. Why not? Don't do that.
So I have
Yeah, well, there was Steve.
Yes, so I just wanted to ask so there's quite a few differences between your model and the biological reality. There's the issue about whether or not the parameter regime is right, but the actual dynamics of the species is somewhat different. And I think in your model that you have a sort of a cyclical symmetry between the species, but that certainly isn't the case in reality. And also the dynamics that you've described are sort of chemical dynamics where one bacterium kills another bacterium. That also isn't what happens really in reality either, because they're interacting through the medium of a poison and such like. So there's quite a few different ways in which you can just
I also.
and one of them would be to write down rather different population dynamics that represent the biology more faithfully. Would you get the same behavior in that kind of model, do you think?
So I wouldn't take this model too seriously in the sense that it's a metaphor, as we heard. So it captures the cyclic thing, but that's it, right? I mean, there are parameters, and you are absolutely right. I mean, the way how this guy interacts with this one is not the same as how this guy interacts with this one. So what we try to do is to say that this guy is releasing poison, and when you release poison, you can kill more than one, right? You just don't simply interact with your nearest neighbors, and that's it, right? And but this seems to the cycling population, the fact that you obtain spirals seem to be robust. So quantitative, there are quantitative differences, but this is something that we checked when we have been asked to check. So that's something that survives.
But the also bacteria don't live on a lattice.
Yeah,
so
sure,
For instance,
obviously, yeah,
the
sure.
non-linear diffusion that you're getting is because of the lattice
I agree, there are various.
yeah. So
Yep.
a similar modelling continuum might not have that. So
Yeah, sure.
So, and I just want to ask something completely different.
Sure.
Which is, to what extent are your results related to Turing patterns?
Two?
To Turing patterns in a reaction diffusion, because you know, for Turing you need something like something that interacts with each other in a positive and a negative way, and some positive feedback, and then you need diffusion.
Yes.
Right. And if you look at this triangle, you basically get the same thing, right? Because they are all interacting negatively, so this means C is actually interacting positively with R, because it kills the killer of R, right? And R is going back and interacting negatively. And it also has some positive feedback to C, because it kills away the S, right? So in a way, it sort of reminded me of a typical Turing.
Yeah, well, the Turing mechanism is different. Well, this mechanism for pattern forming is different than Turing. Here, it's really related to this cyclic competition and the fact that you have the underlying mechanism is this Hopf bifurcation that you have. So the math is different. So, but it's true that, well, Alan did a lot of work on these Turing patterns, and
It's just a different, it's patterns, but it's different mechanisms.
yeah.
Yeah, but what I'm saying is that the mechanism actually reminds me of the Turing mechanism.
I think it's different.
It's different, yeah. And I would think that noise would have much more impact on Turing patterns. So here, basically, as what I showed you, that what I showed you is that noise had very limited impact, right? Whereas in systems characterized by Turing patterns, I mean, often noise can expand the region in which you have this Turing instabilities, if I'm right. Yeah. So that's something that Alan, also Nigel did a lot. Nigel Goldenfeld did a lot, but the mechanism is different.
Okay, well, thanks.
Okay.